Why your shower can never stay at the right temperature. Every morning starts the same way. You wake up, walk into the bathroom, and turn on the shower without thinking. It should be simple, right? Instead, the water is freezing cold, so naturally you turn the handle toward hot. But nothing happens. The water is still cold. You wait for a few seconds, still nothing. You start thinking maybe you didn't turn it enough. So you rotate the handle even further toward hot. Suddenly, the water becomes burning hot. You jump back in surprise. Now you panic and immediately turn the handle back toward cold. Once again, nothing changes. The water stays hot for several more seconds. Then suddenly the water becomes freezing cold again. You keep adjusting the handle. Too hot, too cold, too hot, too cold. It feels impossible to find the perfect temperature. Why can't something as simple as a shower keep the temperature where you want it? Surprisingly, this isn't a plumbing problem. It's actually a control problem. Your shower has all parts of a control system, a process, an input, an output, and even a delay. When you move the shower handle, the hot water doesn't reach you instantly. It has to travel through the pipes first. That delay, my friend, is the real reason why everything goes wrong. While you are waiting, your brain thinks nothing is happening, so you keep making bigger and bigger adjustments. Because the hot water arrives late, your brain keeps asking for more heat. By the time the water finally responds, you have already asked for too much. Engineers call this overshoot. Then you try to fix the mistake, but you're still reacting to old information. So you overcorrect again and again. This endless cycle is called oscillation. Fortunately, engineers solved this problem a long time ago. Instead of reacting like a human, machines use something called a PID controller. But how does a PID controller know exactly how much to adjust without overshooting, without oscillating, and without making the same mistake we do? Let's see how PID fixes the shower. Imagine replacing your brain with a much smarter controller. Instead of guessing, it measures the water temperature hundreds of times every second. It compares the actual temperature with the temperature you want, then decides exactly how much to move the shower valve. That controller is called a PID controller. PID stands for proportional, integral, and derivative. Each part has a different job. The first part is the proportional control. It asks only one question: how far am I from the desired temperature? If the water is much too cold, it makes a large adjustment. If it is only a little cold, it makes only a small adjustment. So big error, big correction, small error, small correction. That sounds perfect, right? But there is a problem. As the temperature gets closer to the target, the error becomes smaller. Smaller errors mean smaller corrections. Eventually, the controller stops changing the valve, even though the water is still a little colder than you wanted. That's why proportional controller alone usually leaves a small error. That's where integral control comes in. Instead of asking how wrong am I right now, it asks how long have I been wrong. Every second the water stays too cold, it remembers. Those tiny errors begin to add up. Eventually, the controller says we have been cold for too long, and it adds a little more heat. Thanks to the integral term, the remaining error slowly disappears. Instead of stopping a little short, the water finally reaches exactly the temperature you asked for. Unfortunately, integral control can sometimes become too enthusiastic. While it's busy correcting the past, the temperature is still changing. Suddenly, you've gone too far again. This is where the final piece arrives: derivative control. It doesn't care about where the temperature is, it cares about how fast it's changing. If the temperature is rising very quickly, it knows overshoot is coming, so it starts slowing things down before the mistake happens. Think of PID as three teammates. P reacts to the present, I remembers the past, whereas D predicts the future. Alone, none of them is perfect. Together, they produce smooth and stable control. Now compare this with the shower from the beginning. No panic, no guessing, no endless turning of the handle. The controller makes tiny adjustments, reach the perfect temperature, and keeps it there. That's the power of a well-tuned PID controller. Now take a moment and think about what you have just seen. You already understand how a PID controller works. When the water was far from the desired temperature, you saw why proportional control makes large corrections. When the temperature stays slightly too cold for a long time, you saw why integral control remembers the past and removes the remaining error. And when temperature starts changing too quickly, you saw how derivative control slows the response before it overshoots. You didn't need an equation to understand any of that. You understood it by watching a simple shower. So now, let us put everything you have learned into one equation. It may look complicated at first, but every term represents an idea you already know. P reacts to the error you have now. I remembers the errors you have had in the past, whereas D predicts where the temperature is heading next. Together, these three actions produce smooth, stable, and accurate control. And that's why the PID controller has remained one of the most successful control algorithms ever developed. Although more advanced control methods exist today, the PID controller remains the benchmark against which many new control strategies are measured. Understanding PID is therefore a fundamental step toward understanding modern control engineering.